PBKDF2 is a key derivation function that is part of RSA Laboratories Public Key Cryptography Standards Series, specifically PKCS number 5v2.0, also published as Internet Engineering Task Force's RFC 2898. It replaces an earlier standard, PBKDF1, which could only produce derived keys up to 160 bits long. PBKDF2 applies a pseudorandom function, such as a cryptographic hash, cipher, or HMAC to the input password or passphrase along with a salt value and repeats the process many times to produce a derived key, which can then be used as a cryptographic key in subsequent operations. The added computational work makes password cracking much more difficult, and is known as key stretching. When the standard was written in 2000, the recommended minimum number of iterations was 1000, but the parameter is intended to be increased over time as CPU speeds increase. Having a salt added to the password reduces the ability to use precomputed hashes for attacks, and means that multiple passwords have to be tested individually, not all at once. The standard recommends a salt length of at least 64 bits. Key derivation process. The PBKDF2 key derivation function has 5 input parameters. dk equals PBKDF2, PRF, password, salt, c, dk len. Where PRF is a pseudorandom function of 2 parameters with output length h len, password is the master password from which a derived key is generated, salt is a cryptographic salt, c is the number of iterations desired, dk len is the desired length of the derived key, dk is the generated derived key. Each h len bit block t of derived key dk is computed as follows. dk equals t1 t2. t dk len len, t equals f, password, salt, c, I. The function f is the XOR of c iterations of chain PRFs. The first iteration of PRF uses password as the PRF key and salt concatenated with I encoded as a big endian 32-bit integer. Subsequent iterations of PRF use password as the PRF key and the output of the previous PRF computation as the salt. F, password, salt, c, I, equals U1 U2. Ug, where U1 equals PRF, password, salt int 32be, I, U2 equals PRF, password, U1. Ug equals PRF, password, Ug1. For example, WPA2 uses dk equals PBKDF2, HMAC SHA1, passphrase, site, 4096, 256. Implementations, OpenSLC implementation, OpenBSD-C implementation, Polar SSL-C implementation, CyASL-C implementation, ActionScript 3.0 implementation, .NET's built-in function, C implementation, Delphi Free Pascal implementation, Erlang implementation, Go implementation, JavaScript implementation slow, less slow, fast, benchmark, Java implementation, Python implementation, Perl implementation, Ruby standard library, Ruby implementation, REBOL2 implementation, PHP implementations, native, pure PHP implementation, Scala implementation, systems that use PBKDF2, Wi-Fi protected access used to secure Wi-Fi wireless networks, Microsoft Windows Data Protection API, Open Document Encryption used in OpenOffice.org, WinZip encryption scheme. LastPass for password hashing. Dashlane for password hashing. Apple's iOS mobile operating system, for protecting user passcodes and passwords. Mac OS X Mountain Lion for user passwords, the Django Web Framework, as of Release 1.4. The MODX Content Management Framework, as of version 2.0. The encryption and decryption schema of Zend Framework, to generate encryption and authentication keys. Cisco iOS and iOS XE Type 4 password hashes. Disk encryption software, file system encryption in the Android operating system, as of version 3.0. FileVault from Apple Computer, FreeOTFE. Also supports mounting Linux volumes under Windows. LUKS, TrueCrypt, Diskcryptor, Cryptographic Disk, GEOMELI module for FreeBSD, Softrade Crypto for OpenBSD, ENCFS since v1.5.0, GeoUB2, alternatives to PBKDF2. One weakness of PBKDF2 is that while its number of iterations can be adjusted to make it take an arbitrarily large amount of computing time, it can be implemented with a small circuit and very little RAM, which makes brute force attacks using ASICs or GPUs relatively cheap. The BCOYPT key derivation function requires a larger amount of RAM and is slightly stronger against such attacks, while the more modern script key derivation function can use arbitrarily large amounts of memory and is therefore more resistant to ASIC and GPU attacks. References: Windows Data Protection. NAI Labs, Network Associates, Incorporated. Microsoft Corporation. October 2001. Archived from the original on April 16, 2007. AES Coding Tips for Developers. WinZip. July 21, 2008. Retrieved September 7, 2013. BRG main site. WinZip.com. Retrieved September 7, 2013. Security. LastPass, How We Do It. LastPass. Retrieved June 13, 2013. LastPass security notification. LastPass. May 4, 2011. Retrieved June 13, 2013. Our security model in a nutshell. Dashlane, Incorporated 2014. Retrieved March 9, 2014. Protection of user data in Dashlane. Dashlane Security White Paper. Dashlane, Incorporated. November 2011. Retrieved March 9, 2014. IO Security, May 2012. Apple Incorporated, How Django Stores Passwords. Django 1.4 Documentation. March 23, 2012. Retrieved July 31, 2012. Encrypt-decrypt using block ciphers, Programmer a Euro Unregistered Trademark S Reference Guide of Zen Framework 2. Worldwide. Cisco Security Response, Cisco iOS and Cisco iOS XE Type 4 Passwords Issue. Tools.cisco.com. Retrieved September 7, 2013. Notes on the implementation of encryption in Android 3.0, September 2012. Android Open Source Project. http, crypto.nsa.org 23c3 Valve Fault PDF, Header Key Derivation, Salt, and Iteration Count. TrueCrypt User a Euro Unregistered Trademark S Guide. TrueCrypt Foundation February 7, 2012. Retrieved June 8, 2013. A.B. Colin Percival. Script. As presented in Stronger Key Derivation via Sequential Memory Hard Functions presented at BSDCA 09, May 2009. New 25 GPU monster devours passwords in seconds. The Security Ledger. December 4, 2012. Retrieved September 7, 2013. External links. RSA PKCS number 5 a Euro RSA Laboratories PKCS number 5 v2.0. Multiple formats, and test vectors. RFC 2898 a Euro specification of PKCS number 5 v2.0. RFC 6070 a Euro test vectors for PBKDF2 with HMAC SHA1. NIST Special Publication 800-132 Recommendation for Password-Based Key Derivation.